Hi class, welcome to exercise 3G scientific notation. Your examples and pre-learning for this class are example 17, converting from scientific notation to basic numerals. And the pre-learning for this is questions 1, 2 and 3 in the new book and questions 4 and 5 in the old book. And we only have one other example for this exercise, and that is example 18, which is converting to scientific notation using significant figures. And the pre-learning for this example is questions 4 and 5 in the new book and questions 6 and 7 in the old book. For all students who've completed Year 9 or Preparatory Maths, this lesson will be revision. So for this reason, I'm going to move quickly through the introduction and the examples. But for those students who work hard to become very confident with the skills learnt in this class, there is a great reward in the enrichment questions. You're going to get to use the most famous equation by the most famous scientist. That's right, Albert Einstein, with that equation, E equals mc squared. But if you're not interested in that, then Mr. Einstein has something to say to you. Well, that's a bit rude. Don't worry, calm down. Don't get so sensitive. Albert is just a bit of a joker, and it's quite okay with you not wanting to work with his amazing equation. See, he was only joking. Also, not only do you have Einstein in your enrichment, I will give you a bonus challenge at the end. I think it's interesting and it'll give you a good perspective on how powerful exponentials are. But please make sure you do the lesson first. Please don't turn me into Grover. This Grover. I really love this book. Okay, we better finish this and get on with the introduction. Have you heard the saying, orders of magnitude before? Well, it comes from the concept of scientific notation. In scientific studies, you might be researching the very big or the very small. When we look up at the night sky, we often wonder how far away things are. The numbers to describe these distances are, well, out of this world. What about the moon? The moon is 384,400 kilometers away. What about the sun? The sun is nearly 150 million kilometers away. What about the closest star, Alpha Centauri? Alpha Centauri is 40 trillion kilometers away. The closest large galaxy to us, Andromeda, that is, well, forget about it. I'm not going to fit it on the page, but let's put it this way. Alpha Centauri is 4 light years away, and you can see how many kilometers that is. The Andromeda galaxy is 2.5 million light years away. So let's leave that there. So that's the very large. On the other hand, the very small is commonly found in chemistry and biology. For example, an average human cell. This weighs 0.00000001 grams. We've also got the E. coli bacteria, and this weighs 0.0000000001 grams. So this is getting tiny. What about a water molecule? One water molecule is 0.00, I'm just going to write it down. That's tiny. This is obviously getting laborious to write out. So we need to find a shortcut, and this is where scientific notation comes in. So starting with the very big, I could rewrite the moon as 3.8 times 10 to the 5. And the distance to the sun is 1.5 times 10 to the 8. And the distance to Alpha Centauri is 4 times 10 to the 13. So the reason why the moon is 10 to the 5 is we can see that 1, 2, 3, 4, 5. This 3 signifies 100,000 or 300,000. So that is 10 to the 5. Similarly, the 14th digit is 10 to the 13. So can we use some of this to write out the small? So the human cell, as you can see, our leading term is 1. I can write it as 1 times 10 to the minus 9. And this is because we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that 1 signifies the spot where we have 10 to the minus 9. Similarly for E. coli, that is 1 times 10 to the minus 12. And the water molecule is 3 times 10 to the minus 3. So we can see we have negative indices for very small and positive indices for very big. So obviously I've given it away a bit, but the question is, how do we convert numbers to scientific notation? So you might have noticed we raised everything to the power of 10. So why do we always use 10 as the base? Well, I'll give you a hand. No, really, look at your hands. The reason we have 10 as the base is because we have a base 10 number system, which is because we've all got 10 fingers, hopefully. So the key to our base 10 system is 10 to the 0 equals 1, 10 to the 1 equals 10. 10 to the minus 1 equals 1/10 or 0.1. 10 to the 2 or 10 squared equals 100. And 10 to the minus 2 equals 100th or 0.01. To convert to scientific notation, we find the first term and its place value determines the index for base 10. So let's use the moon distance for example. So the first digit to the left of the decimal, which had the distance 384400.0. So the first digit to the left of the decimal has a magnitude of 0, in this case the actual digit 0 as well. And because the leading digit is to the left, we can count how many decimal places we need to move to make 3 the leading term. So starting at the decimal place, we have 1, 2, 3, 4, 5 decimal places. So we have 1, 2, 3, 4, 5. And we can place a decimal place right here. So that means the first position had a magnitude of 0 and the last position has a magnitude of 5. So this means we can now write that as that this number here is actually 3.84400 times 10 to the 5. In this case, we have 4 significant figures. What would 5 significant figures look like? Well, that would be 3.8440 times 10 to the 5. So sometimes to get the amount of significant figures they want, you need to include a 0. If they ask for less significant figures than the amount of figures you've actually got in the number, then you're going to need to round. So in this case, if we were asked to get 3 or 2 significant figures, the 4s wouldn't round up or down, they would just stay as they are and go to 0. However, if we were asked to provide 1 significant figure, we'd have to round from 3.8 up to 4. Anyhow, you can find more of these masses and distances at these wiki pages. But as fascinating as some of these are, don't let the scientific notation mislead you. For example, 10 to the 26 is 1,000,000 times bigger than 10 to the 20, which is already a huge number. So yeah, these orders of magnitude can catch you out because you can think, oh, not a big difference between 20 and 26. Anyhow, let's move on to the sections with some examples. Okay, I think you'll find this fairly easy. All we're going to be doing is multiplying by powers of 10. So when you do that, you really only need to move the decimal place. You don't even need a calculator. When we multiply by a positive power of 10, we move the decimal point to the right, adding zeros when we run out of numbers. For example, 3.2 times 10 to the 3 is equal to a number that has 3 and 2 in it, but the decimal place, instead of starting here, has to move here, 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 down to the right. So we need to add 2 more zeros. When multiplying by negative powers of 10, we move the decimal point to the left. Once again, we'll have to add zeros for decimal places where necessary. So for example, we'll use 3.2 again, but this time we'll multiply it by 10 to the minus 3. So that's going to equal a number that has a 3 and a 2 in it, but because we've got minus 3 in the powers of 10, we're going to move the decimal places 3 places to the left. So we start here, and then move here, here, here. And the new decimal place belongs right here. Now we need to add zeros in these gaps, and we also need a 0 to the left of the decimal point. So we now have 0.0032. So in the past, you've probably learnt this as multiplying or dividing by tens and how that changes a decimal place. In this unit, you've learnt that 10 to the minus m is the same as 1 on 10 to the m. So basically, it is the same as dividing. And by it, I mean negative powers. Alright, that's enough talk. In example 17, we need to convert the following numbers that are in scientific notation back into basic numerals. In part A, the number is 5.016 times 10 to the 5. So if I rewrite the first 4 digits, 5016, I know the decimal place is going to start next to the 5, and we're going to move it to the right 5 times because we're multiplying it by 10 to the 5. So that's 1, 2, 3, 4, 5. So a new decimal place is here, and you can see that we need to fit 2 zeros after the 6. And now we end up with 501,600. So it really is that straightforward, okay? Particularly when we're using positive powers. Alright, let's do part B, where the number is 3.2 times 10 to the minus 7. So that means we're going to move the decimal place 7 places to the left. So let's start off by writing the digits we have got, which is a 3 and a 2, leaving some space to move our decimal place to the left. And we know that our decimal place is currently between the 3 and the 2. And we need to move it 7 places to the left because of 10 to the minus 7. So that's 1, 2, 3, 4, 5, 6, 7. And you can see that's still not enough room. So let me move this equal sign. And our new decimal place is here. So we need to fit 1, 2, 3, 4, 5, 6 zeros. And because we have a decimal place there, it's normal to put a 0 on the other side of the decimal place. And now I can rewrite that as 0.6032. Hopefully you'll find some shortcuts soon. Like for example, because it's 10 to the 5, I know there's going to be 6 digits. And because it's 10 to the minus 7 in B, I know that there will be 6 zeros afterwards. Alright, so you should pause the video now and do questions 1, 2 and 3 in the new book and questions 4 and 5 in the old book. And I'll see you in the next section. In this section, we're going to be converting to scientific notation using significant figures. So this is slightly tougher, but if you remember from the introduction, you just need to find the magnitude of the leading digit and then you select the required amount of significant figures. This might occasionally require some rounding from you. Alright, so without further ado, in example 18, we're asked to convert the following numbers to scientific notation using 3 significant figures. In part A, the number is 5,218,300 or 5218300. If I write the magnitude of the powers of 10 to each digit underneath them, it'll make it clear what we need to put as our power. Because we have positive numbers here, the first one starts with a 0, and then we have 1, 2, 3, 4, 5, and 6. So because this 5 is equivalent to 10 to the 6, then I can rewrite this whole number as 5.2183 times 10 to the 6. But the question asks us just to get 3 significant figures. We need to check the last one and then the digit after that to see if we need to round. And 18 rounds to 20. So I can now rewrite that as 5.22, because I'm rounding up the 1, times 10 to the 6. And in part B, we've got 0.004203. And because we're to the right of the decimal place here, we know we're going to have negatives. Let's write down the corresponding powers of 10 for each digit. So we start off with -1, -2, and the 4 is where the -3 is. So that means I can convert this number to 4.2031 times 10 to the -3. Once again, we need to be concerned with the amount of significant figures. So we're looking for 3 significant figures. And at the end, we have a 0 and a 3 after that. So we need to round 03 to 00. So that means when I have 3 significant figures, that's 4.20. And of course, times 10 to the -3. And let's just highlight one more time that we have 3 significant figures. Okay, that's it for this example. You can see that on the one hand, it's fairly straightforward. However, there's plenty of room to make mistakes about the magnitude, especially for small numbers that have negative magnitude. And this is because negative powers begin counting from -1 as we move to the right, and positive powers begin counting from 0 as we move to the left. I'm sorry if it sounds very repeaty going on about the magnitudes and the significant figures, but not only is it the point of this lesson, I've always found them difficult. They can be quite confusing. That is because significant figures includes the number to the left of the decimal place. I always have it in my mind that the amount of significant figures they're asking for is actually the amount of decimal places. So watch out, that's a really easy mistake to make. But anyhow, pause the video now and you can do questions 4 and 5 in the new and questions 6 and 7 if you have the old book. And once you've completed that pre-learning, come back and you can see the summary. Okay, welcome to the summary. Now, if you want to consider this lesson a success, you will be able to understand that very large and small numbers can be written in a shorthand form. Know the general form of a number in scientific notation. Be able to convert between scientific notation and basic numerals. Know the meaning of the term significant figure. Be able to round a number to a desired number of significant figures. And finally, to know how to use technology in working with scientific notation. Alright, so we've definitely covered all of those fairly well, except for the last one. So that is definitely something we need to do in class. But the main thing to say about that is, when you see E in a calculator followed by a number, that's its order of magnitude as far as scientific notation goes. Alright, so as I promised at the start, I have a final challenge for you. I love this one. So while the solution isn't strictly about the powers of 10, it will still remain relevant to this lesson because I'll express small and ridiculously large numbers using scientific notation. Alright, here it is. A piece of paper is 0.1 millimeters thick, or a tenth of a millimeter, which is 1 times 10 to the minus 4 meters. So if you fold a piece of paper in half, it's now twice as thick. If you fold it in half again, it's 4 times as thick. And on you can go, assuming that you can fold a piece of paper as many times as you want. Our current understanding and measurements lead us to believe that the diameter of the observable universe is 8.8 times 10 to the 26 meters, which is about 4.6 billion light years. Now imagine a piece of paper that was so big you could continuously fold it until the thickness of this paper would span across the whole observable universe. So my questions for you are, how many times would I need to fold the piece of paper to make it that thick? However, you can start with some other questions first if you like. So the first thing you could do is figure out how many folds would it take to make the stack of paper as high as 5 meters? And how many folds would it take to reach the top of Mount Everest, which is about 8 times 10 to the 3 meters high? And how many folds to reach the moon, which is about 3.8 times 10 to the 8 meters? Anyhow, you can give me your results and calculations to any of these distance in the comments below or in class. And as always, if I don't see you in class next, I'll see you in the next video. Bye.